Welcome, ViniPhysics here. Today I'm going to talk to you about the MythBusters episode, Indy car specials, a manhole cover myth, and it is from season 14, episode 4. So what they explored in this episode was the myth that an Indy car traveling at 150 miles per hour could generate sufficient aerodynamic forces to lift a 130-pound manhole cover. So let you watch the introduction, and then I will discuss the physics.
Indianapolis Motor Speedway and its Indy car versus manhole cover. We're going to bring an Indy car up to full speed and see whether its aerodynamics are powerful enough to suck a manhole cover right out of the ground. Oh, look at that. A manhole in the middle of nowhere.
It's not in the middle of nowhere. We are in the middle of the Indianapolis Motor Speedway complex, and they've done this just for our experiment. Cool. I'm going to get to work.
And there's plenty to do. As well as installing a camera, they're hooking a force gauge up to the cover to measure how much it moves, if at all. But the star and the source of this myth is the cover. Beautiful. They made this one themselves from clear plastic so sunlight gets through for the cameras. And it weighs 30 pounds.
I know what you're saying. You're saying, Adam, your see-through manhole cover doesn't weigh near as much as a cast-iron manhole cover. How can this be an accurate test? And you're right, except that we've already thought of it. We are going to make this weigh as much as this with these 4 chunks of 4-inch diameter steel. We are going to bolt them to the see-through manhole cover, and it will weigh exactly as much as a cast-iron manhole cover. We got you covered. There it is. A scientifically accurate manhole cover.
And while nobody knows how this full-scale test will pan out, they've all considered the possible perils of success.
When the car comes down this road at 150 miles an hour and drives over it, it might just lift out of the ground. And that could be very bad for an instrument as precise as an Indy car with a ground clearance of as low as 7/8 of an inch. So Jamie right now is tying some very high strength line so that when we have the manhole cover in place, it can only lift about 1/2 inch. It won't be able to actually hurt the car, but we'll still be able to measure the force that it's actually being pulled up with.
Logan Gomez is our driver, or should I say chauffeur, because Adam will also have his butt just an inch off the bitumen.
Okay, so let's analyze the physics. The first question I ask myself is if there is a vacuum, a complete vacuum above the manhole cover, meaning all the air has been evacuated by the car. Okay, so let's do this. Air pressure from below, say due to 1 atmosphere pressure, so we have a force from below. And the force from, normally you'd have a force from above because you also have air above the manhole cover. But I'm going to assume that the car does create a complete vacuum above the manhole cover. So based on this scenario where you've got 1 atmosphere of pressure below the manhole cover and no air pressure above it, if I can do the math and prove that that's insufficient to lift the manhole cover, then there'd be no reason to do the experiment. So let's do the math. Okay, so again, we've got 1 atmosphere of pressure below the manhole cover. Of course, you've got the weight of the manhole cover, and that gives you a net force equation that looks like this. Force above minus the force below minus the weight, and that's 130 pounds, and that's equal to the net force, so mass times acceleration. Okay, so what it says, I'm going to assume that there's, actually this is backwards, force below minus the force above. Okay, so again, I assume that you wouldn't have a force above because the car takes all the air with it. So the force below due to 1 atmosphere is going to be 4471 pounds. Okay, so minus 130 pounds is equal to mass times acceleration. Okay, so that's a big number, and that's a big difference. So if we divide both sides by the mass of the manhole cover, we'll get the acceleration of the manhole cover. Okay, so a couple things I need to do is I need to show you where that number came from, 4471. Okay, there's an equation which relates pressure to force and area, and it is this. Okay, so the pressure of air at sea level is 14.7 pounds per square inch. Okay, the area of a manhole cover, this would be the radius, looks like a circle, right? Manhole cover is basically a circle, radius R. And R for your standard manhole cover is 9.84 inches. Okay, so the area of a circle, right, area is equal to pi r squared. Okay, so let's plug that in here for area. So we use pi times 9.84 inches squared. Okay, so that's going to be the force from below due to air pressure. Okay, multiplying that together, you get the 4471. Force from below. Okay, the mass of the manhole cover. Okay, weight and mass are not the same, right? The weight of the manhole cover is 130 pounds. And that's equal to mass times acceleration due to gravity, working here in feet per second squared. Okay, so if we divide both sides by 32 feet per second squared, we get mass. Okay, and that turns out to be 4.1 in units of slugs. So 4.1 slugs. Okay, so that's what we're going to put back up here. Okay, so 4.1 up here. Okay, when we do that math, we get a really big number. The number is 1059. So the acceleration of the manhole cover, if there's a complete evacuation of air above it, is 1059. Okay, so we come down here. A is equal to 1059 feet per second squared. Okay, so that's a huge number. But what is that in terms of the distance the manhole cover would rise? Okay, let's figure that out. Okay, there's an equation that you can derive from Newton's second law for constant acceleration, and it looks like this. Displacement in the vertical direction is equal to 1/2 acceleration times time squared. Okay, so the amount of displacement, 1/2 times 1059 times t squared. Okay, time is the amount of time for which this manhole cover is accelerating, and I argue that that is the time that the car is above the manhole cover. Okay, so here's the manhole cover. It's got a diameter of 1.64 feet. Diameter now, 1.64. Okay, and here's the car. The car happens to have a pretty significant length of, Indy car is 16.8 feet. Okay, pretty long car. Okay, so I'm going to use a D. It's my D. So the length of the car, let's call that L. The length of the car that's always above the manhole cover turns out to be the length of the car, which is 16.8 feet, minus the diameter of the manhole cover, minus 1.64. Okay, so the time, the duration that some part of the car is always above the manhole cover is going to be, we can use speed times time equal distance. So speed times time is equal to length of the this length will give us the time that this manhole cover is completely covered by some part of the car. Okay, so let's solve for time. Time is equal to L over S. Okay, so it's going to be this right here, that's feet. So 16.8 minus 1.64 feet divided by the speed of the car. Okay, so the speed of the car in miles per hour, 150 miles per hour. Okay, if we multiply that by two conversion factors, one is 5280 feet per mile, and the other conversion factor is 1 hour, it's 3600 seconds. We get speed in feet per second, and we need that because this is in feet. Okay, so that turns out to be 220 feet per second. Okay, so I'm going to plug that in here, 220 feet per second. Okay, and I get a time of 0.07 seconds. Okay? Okay, now I can go back to this equation and plug that in for the time in which the acceleration of the manhole cover occurs. So 0.07 squared. And plug that into your calculator, and that's 2.6 feet. Okay? So the math says that if you do have a complete evacuation of air above the manhole cover with 1 atmosphere of pressure below it, and that's essentially what their claim is. They're claiming is there enough pressure differential? And I went to the extreme and said, what if there is a complete vacuum above? Math says that the manhole cover should rise 2.6 feet. So let's see what happens.
The car is a tandem.
This is where the literal rubber meets the literal road meets the manhole cover.
This Indy racing experience car exerts just as much downforce as the real thing. Target speed for today's test is 150 miles per hour. Pretty much the top speed for a city street circuit.
In lieu of a steering wheel, my fleet is equipped with these. We call them HCHs. They're known as holy crap.
Okay, they ran this at two different speeds. One, they ran the Indy car at 100 miles per hour above the manhole cover, found no movement of the manhole cover. The second one was at 150 miles per hour. So I'm going to advance this to that scene.
It's for Logan to crank up the speed to 150.
Hey Adam, I could try one from the end of the runway, see if we could get a bit more speed.
Let's do it!
With Adam latched tight to his HCH, Logan whips the horses up to a full gallop.
149.
Beautiful!
Shall we go look at the evidence?
Let's go look at the evidence. All right, my favorite part, high-speed review.
I'm not seeing it.
Nothing, absolute nothing. It did not budge.
Nope. Bump.
That's pretty definitive.
I think so.
We had a clear manhole cover weighing the same as a cast iron manhole cover, and Logan passed over it several times at a top speed of almost 150 miles an hour. And how much movement did we see on it? Buckets. Now we're going to pull all the weight from it. So
Okay, so they saw no motion of the manhole cover. So what does that tell us? What can we conclude? Well, we can definitely conclude that there's not a complete vacuum above the manhole cover, because if that were the case, it would have moved a significant amount and we would have seen it. We can't assume that it didn't move at all. It's possible their instruments just couldn't measure a really tiny amount of movement. So that was experiment number one. Experiment number two, they went ahead and they dropped the weight of the manhole cover, and they ran again the Indy car at 150 miles per hour above the manhole cover. So take a look at my next video on that for experiment number two. Out of that experiment comes a couple of experimental facts that we'll use to go back and revisit experiment number one and will enable us to conclude if the manhole cover really did move, they just didn't have sensitive enough instruments to measure it. And think about it, if the manhole cover moved a nanometer, they probably couldn't measure that. That's what my math will enable us to determine, if it moved at all. So check out the next video on this episode.